data abstraction is the main organizing principle for building complex software systems. Without data abstraction, computing technology would be nowhere. It would stop dead in its tracks. We would have nothing compared to what we have today. So let's now study data abstraction and how it's supported by the programming language. The first step toward data abstraction is called encapsulation. And after that, we will see how to make different forms of data abstraction using the language concepts we saw, in specifically higher order programming, static scoping, and explicit state. So the first step toward data abstraction is encapsulation. Encapsulation, let me introduce it with an example. Assume you have a television set and it's not enclosed in a box. All the interior circuitry is exposed to the outside. Well, it's lighter, takes up less space. No? So, that's good, right? Well, no. It's dangerous for you. If you touch the circuitry, you might get a shock. 220 volts can be deadly. It's also bad for the television set. If you spill a cup of coffee inside it, you can provoke a short circuit and break it. And it's even worse. If you are an electronics hobbyist and you like building circuits, you might be tempted to, quote unquote, improve the television's internal circuitry, which usually is a bad idea. So, in fact, it can be a very good idea to put the television in an enclosing box. A box will protect the television against damage, and it only authorizes proper interaction, so you can actually guarantee it works. So in a program, the same thing holds. Here, let's say you have an implementation of a stack here. New stack returns nil. Pushing X on the stack S returns X bar S. Popping X from the stack returns S.1 as the top, and the result of the stack is S.2. And there's a check whether the stack is empty. So this implementation uses lists to represent stacks. Well, this implementation is not encapsulated. The lists are exposed to the rest of the program. In fact, it has the same problems as a television set without an enclosure. The lists are not protected. That means you can read stack values without the implementation knowing that you're doing it. You can also create stack values, new ones, because they're just lists. And the implementation does not know that you've created a fake stack value. So the implementation cannot guarantee that the stack will work. There's no way it can guarantee. So in order to guarantee, we must encapsulate. And this leads us to data abstraction. So a data abstraction is a part of a program that has an inside, an outside, and an interface in between. So there's an inside here. There's the outside here, and then there's the interface connecting the two. The inside is hidden from the outside. All operations on the inside must pass through the interface. The data abstraction must use encapsulation. And what is the interface? This set of operations here, up 1, up 2, up 3. Well, it's a set of operations that can be used according to certain rules. So the rules are part of the interface. And the point is that if you use these rules correctly, then you know the results will be correct. If you use them incorrectly, you will not get results. The abstraction probably will not break. It has well-defined behavior, but in order to get correct results, you must use the rules correctly. Final point is that we want the encapsulation to be supported by the programming language. We want to enforce the separation between inside and outside. That's an important thing we're going to see, how to build abstractions such that you can guarantee that you have encapsulation. So the advantages of data abstraction are many. We saw a couple of them already in the previous slides, but we can summarize them systematically. The first and most important one is the guarantee. If you use the interface, if you don't have access directly to the inside, then the abstraction can guarantee that you have correct behavior. That's the first one. The second advantage is reduction of complexity. You don't have to understand the implementation in order to use the abstraction. You only have to understand the interface, which is in most cases much, much simpler. You don't have to understand how to build a car in order to drive a car. You don't have to understand how to build a television set in order how to use a television set. And you can partition a program into many independent abstractions, which greatly simplifies its use. And a final point, which is partly a consequence of the previous one, is that the development of large programs becomes possible. Programs that are too large to fit into the head of one person. Because each abstraction has one person which is the responsible developer of that abstraction. That person only has to know that abstraction and the interfaces it connects to. Okay? That person will implement, maintain, guarantee the behavior, and connect only to the abstractions that are used by that person's abstraction. So if you then partition a large project into abstractions in this way, you can have large teams of developers working together, and it's possible to go to millions, tens of millions of lines of code, where a single programmer can only manage 100,000 lines correctly in their head. If you have a team, you can go to millions of lines. This is how the big, successful software systems that are used in our society have been built. Now, let's go a little bit into the details of data abstraction. There are in fact two main kinds of data abstraction, which are called objects and abstract data types. And they're actually quite different, although any kind of operations can be packaged as objects or abstract data types, but the way that one interacts with them is quite different. So an object groups together value and operations of the data type into a single entity. And an abstract data type keeps the values and the operations separately. So let me just give an example, because this kind of distinction exists very much in the real world. So a television set is an object. It is self-contained. You have it there, you have a set of operations, it has internal state, it does things, you can control it directly, and it provides the functionality directly. So there's only one thing, the television set. An example of an abstract data type is a coin-operated vending machine. The vending machine by itself is nothing. You need coins and the products that it delivers. So you give coins to the vending machine, and it provides with products. So you have the values, which are the coins and the products, and the operations, which are the different kinds of vending machines. So these are two separate things, and together they form one data abstraction. Only a certain kind of coin will be accepted by the vending machine, and only gives certain kinds of products. So the data abstraction also has a protection between inside and outside. So this protection exists both for objects and for abstract data types. So in the rest of this course, we will look at both objects and abstract data types, how they're implemented, and their advantages and disadvantages.